Hey everybody, welcome to this video in which we will be showcasing two different ways in which you can solve the Hamming exercise on the F-sharp track. The Hamming exercise is one in which you get two different strings which represent DNA strands, and you have to return the number of places where they have different letters. So if you look at this example here, there are two strings and they differ in 7 places. So the Hamming distance for these two strands is 7, and that's what we will be implementing. Let's look at our starting point. We are given a distance function. That function takes two string parameters, the strands, and returns an int option type. So it doesn't just return an int. What is this option thing? Well, the exercise only defines the Hamming distance for strings of the same length. So what if we get strings that have different lengths? We somehow have to, we can't do the calculation, so we have to let the caller know that, hey, we couldn't actually do any calculation. We could have returned a magic value like -1 or something like that, but the more idiomatic F-sharp way is to return an option type. So the int option that we return can be one of two values. Either it's none, which means that, sorry, we couldn't compute the result, or we have some with an integer, and that's the actual distance. So the caller then has to look at the actual value that's being returned to see if it's actually successful or not. So they have to be very explicit about it, and we can encode within the type system the possibility of failure of our execution. So let's look at our tests. We see here that if we start out with the Hamming distance for empty strings, it's 0 wrapped in a sum value. So this is a successful execution because both strands have the same length. There's just not any difference. So if you go a bit further along and we have these two strings, they have the same distance, but these have different strands, and so they have sum 9. And then we have a couple of test cases where the strands have different lengths, and then we return none. So that's the basics of our exercise. And let's get started with the two different approaches. The first approach that we will be looking at is a recursive one. So what we're going to do is we're going to write a recursive function. We'll call it doDistance. And note that we have to add the rec modifier. Otherwise, you can't use recursion within the function. And instead of passing in both strands as strings, we're going to pass them in as character lists. And that will make it easier to do pattern matching in a second. So strand 1 is a character list, strand 2 is a character list, and then we'll have a third argument, which is distance, and this will be the distance of the already processed letters. So in the end, this will have the right Hamming distance. And now our return type is an int option, and let's see how we can implement this. So we have both strands as character lists, and we want to process them one by one. We'll use pattern matching for that. And we can pattern match on two values at the same time. To do so, we use match. We'll pass in strand 1 and strand 2 with, and then we can add the actual patterns. So what pattern should we look at? Well, we're dealing with lists, and if you're dealing with lists, you always have to consider the cases where both lists are empty. So let's try and do that. So strand 1 is empty, strand 2 is empty. This means that, well, they have the same length. Otherwise, we would have not gotten here. And this means that we're at the end of our recursion and we can return the distance. So the distance value is an accumulator. It will have the right distance. So we can just return some distance. Then, what do we do if the first strand is empty, but the second one isn't? Well, this means that they have different lengths. So we have to return none. And we do the same thing with the other way around, which is empty second list and non-empty first one will return none. So this is all good. We could call our function and to see if we have any tests passing yet. So we're going to do distance, and then we're going to convert the string to a character list. And as strings are sequences of characters, we can call the sec.toList function on them. So sec.toList on the second strand, and then we have to pass in the initial distance, which is 0. So let's run the tests. and we have some tests passing and a lot of tests failing. And we only have the empty tests passing, so that's fine. So let's see where the actual recursive bit comes into play. And that's in our fourth pattern. And in this pattern, what we want to do is we're going to extract the first letter of both character lists. So, and then see if they are equal or unequal, and then do the appropriate distance updating. So we're going to say letter 1, colon, colon, till 1. And this is the pattern that's being applied to the first strand, so the character list. This is the first letter in the list, and till 1 are the other letters. So everything but the first letter. So we're going to do comma. We're going to do a similar thing for the second strand. So letter 2, colon, colon, till 2. And then we're going to write our implementation. So this is where we actually finally get to do some recursion. There are just two different cases that we have to consider. One is where the letters are equal, and one is where they're not. So if letter 1 is letter 2, then what do we need to do? So if they're equal, the distance stays the same, and we should just continue our recursive processing of the letters, but disregarding the first letter. So we're going to call do distance, and we're going to call it with till 1. So this is everything but the first letter, and till 2, and then with the same distance, because the distance doesn't change because the letters are the same. And this is the crux of our algorithm. We are processing the rest of the list. So the list keeps on getting smaller and smaller and smaller until we reach one of the first 3 cases. So the second case, the else branch, is the letters are unequal. We'll still have to continue processing things, so till 1 and till 2, but this time the distance is changing because the letters are unequal. So we have to increment the distance by 1. And actually, this is it. So if we run the test, we should see all of them passing, and we do. So that's great. There is one way in which we could rewrite this a bit. I'm going to put this in comments. And what I'm going to do is, instead of that, I'll be changing this to have a guard clause. So a guard clause is, you can have a pattern, and there is a Boolean thing that has to match before you're going to execute its code. So we're going to say pattern deconstruct both strands, and we're going to say, and then when the letter is equal to, the first letter is equal to the second one, we're going to execute this code. And then we're going to do the second option, which is the letters are unequal. And if they're unequal, we're going to run this code, and that's the code that increments the distance. So we can rerun it, rerun the test. There we go, and it still passes. Obviously, this bit is always true because otherwise the patterns are the same. The only thing that changes is the Boolean condition. So we can omit this. So rerunning should still be the same. And then we're not even using the letters. So what we can do is we can say, hey, we're not really interested in the letters themselves. We can just use underscores and then run it again. And it still works. So whether or not you prefer this version or this version is up to you. There are arguments for both. And you can basically decide for yourself. Just remove it for now and see. This is our final setup for our recursive approach. In the second approach, we won't be doing manual recursion, but what we will be doing is using some of the built-in functions in the sequence module. The first thing that we want to get out of the way is the error case. So let's start with that. If strand1.length is unequal to strand2.length, then we'll return none. And we have to satisfy the compiler because now we haven't returned a value from the else branch, and F# requires the same type of value to be returned from both branches. So we're going to do just none. We'll run the test. And we have some passing tests, and these are all the tests that validate that if the lengths are unequal, we should get none. So then we'll need to use some functions to process the strands letter by letter. So the simplest way that you can do this is by using something that's called sec.zip. And what sec.zip does, it takes two sequences and it will return a sequence of pairs. And those pairs will be in the same order. So you will have the first element that's returned is a pair of the first element of the first sequence and the first element of the second sequence. So these will be, in our case, the first letters, then the second letters, then the third, etc., etc. So we'll pass in strand 1 and strand 2, and we'll call this letter pairs. So this is a sequence of tuples that have 2 characters. Then the next step that we can implement is that we're going to find the unequal pairs, and we're going to use the sec.filter for that. So sec.filter takes in a lambda, and it will work on our letter pairs. So this is letter 1, letter 2. So this is a tuple deconstruction, and then we're gonna just filter those where they're different. So we're gonna say letter 1 is unequal to letter 2, and then pass in letter pairs as the argument. So this says take all the letter pairs. We're gonna check if letter 1 and letter 2 are unequal, and then we're gonna keep them. So this is all the unequal pairs. And then finally, the distance is the number of elements in the sequence. So sec.length of unequal pairs, that's what we return. So distance. And as we now have successfully calculated the distance, we have to wrap it in a sum value. And we'll do that. Rerun the tests. And they all pass. So this is a very functional way. Using sec.zip to combine the sequences into a single sequence of pairs, tuples, then use sec.filter to only keep the pairs where the letters are different, and then count them via sec.length. So the final thing that we can do is we can use pipelining, because this is actually the same as the last argument, which means that instead of doing using an intermediate value, we're going to do something differently. I'm going to rewrite this somewhat slightly. I'm going to say pipe this into sec.filter. We're going to remove it here. So this will be as if this value is put into this position. So, and then as the value passed into sec.length is also the latest value, the last argument, we're going to pass it into a pipe too. And we do the same thing with sum. So this is now an F# pipeline using the pipeline operator. So we're going to say sec.zip. The result of that is used as the last argument to the sec.filter function. And then the return value of that is used as the last argument of the sec.length value function. And then the same thing with the sum. So if we rerun our test, it should still all work, and it does. So we now have a very functional way of solving the Hamming exercise using just a couple of built-in functions.